The next, need to record this one. Okay, now it's starting record. Okay, so let's go back quickly one more time. Okay, so we have any function. So derivative is by definition is the signs, how to write it this way could be adding for simply. Later on when we use the more frequent derivative, I really don't want to write this way. I just write a dot on top or write a stretch here. So that means that derivative, f function to x. And the definition is really looking for a rate change is by small change of delta x, how much change of this function is. So eventually that translates in this kind of, if you're graphing it, is really a slope, tangent here. Because whatever change here, delta x, small delta x change, talking about small delta y change, that is the slope definition. And so basically this is the derivatives definition. From here is like last time we have done, it's very easy to calculate like what is x derivative is really 1, and what is this guy's derivative is x, this side. So you can derive those one by using this definition without any issue. Shouldn't have much issue. Okay, and from there then we come another called integral definition. Integral definition is, graphing concept is really talking about the function fx graph here, and you're talking about how to calculate the area underneath this curve from this location to that location. So in that case, it's integral here, and so by definition, is really talking about a sum of all those small stripe, and from with delta x, and y times delta x is really the area of this very tiny narrow of stripe, and then you're adding everything together, and so you're moving from this location to here, adding everything together. In order to make this perfectly accurate, you really need to, same thing, you need like derivative, you need to push delta x to smaller, eventually to 0, and so that's limit. That's called infinite small, and then you are able to get precisely adding up all those slices and approaching eventually exactly the area underneath. So by sign we do this way, that's called the integral this function over x. Eventually, let's say this is the gx. So actually is gx derivative is really fx. So gx derivative, if you go through here, is fx. Okay. So this way, basically, you can see that if what is integral of simple function x is really 1/2 x squared, because this guy's derivative is x, and what is this x power x squared, and the integral is 1/3 x cubed, because this guy's derivative and 1 square. Okay, so this is about general for all the power case. And now, what is integral of cosine x? Last time we already, I sent you later on a strict proof is sine. Sine x derivative is cosine x. Right? Same thing. What is sine x integral? It should be negative cosine x, because cosine x derivative minus sine x. Okay, and there's a couple other things we needed to be familiar with. For example, natural log x derivative is 1/x. You can prove by yourself by use that definition. Okay, And this one's derivative is itself. Okay, all sort of thing. So eventually, basically, people by going through all this definition, people calculate all conventional, all kinds of functions derivative by going through this one. And then we accumulate a knowledge of, we don't need to go every time go back to this definition, calculate the way last time I did, right? Derive why is a sine derivative is cosine. I went 2 pages to prove that, right? And I went y is x power, the derivative is that. I went maybe 3-4 lines to prove that. So once we prove that, use this formula, this definition, so we have all those formula in place, then that build a foundation for us to go moving forward. Every time we can just use that formula. We don't need to go back to prove that anymore, okay? Because as once proved, it's true. So that is how we can using this one. And meanwhile, of course, we know how to do the integral, right? So because integral eventually, when we do any function integral, is really looking for that what that functions, whoever derivative is getting to that function, right? So therefore, as long as you know all the functions relationship from derivative perspective, one function derivative is what, and whose function is derivative this guy, then you are able to build the whole library. Once you have this library, then the whole calculus foundation is become really, really powerful. I will prove you later, okay? So it's really powerful. That becomes, you can do all kinds of very interesting calculations. And, like the one I was hinted before with Frank and Leo, and it's like how later I will try to show you how to solve a question like we call the hanging cable problem. So this case is, you see it every day, but it is a very interesting math and physics problem once you know how to use calculus. For example, like the electricity cables hanging, on the, you drive on the highway, you see the electricity cables hanging between 2 towers. And so what's that shape? It's not a parabola. Okay, people think that is parabola. No, actually it's not parabola. And eventually you'll find it's interesting how to calculate that shape. Oh, and I don't know if you sometimes your parents hanging a rope between two places, locations, and try to hang some, try to dry your clothes. And so what kind of this shape? So what is shape? So we can use this calculus, we can use lots of this calculus knowledge and calculus knowledge to able to derive this, and with perfectly, we can perfectly solve this question. And it's really, lots of those kind of examples later I will show you. I collect some of those simple examples. It makes a learning fun, and you can see how powerful it is, right? So today, actually, we are going to go over some of the example. We are not go over this example because this example is more complicated, because it also requires lots of physics understanding as well. But I will address this one later in probably in several lessons. I'll come back to here. Okay.
Wait, was that question asking you to describe? Sorry. Wait, was that question asking you to describe with an equation the shape of the cable?
Yeah. Basically, it's like, yes, if you're hanging a cable or whatever rope, of course it has a weight, right? Has a weight.
Does that have to do with the center of mass equation?
Say again.
Does that have anything to do with like the center of mass equation?
No. This case, of course, we assume this rope is a uniform rope, right? It's not like somewhere somewhere is thicker, somewhere is narrow. It's a uniform rope. Like typically we use the cable, electrical line, or we use whatever rope we're hanging for drying clothes. And in that case, once you know the mass of the rope, and length of the rope, and so you are able to derive this shape. You can, perfectly, yeah, with calculus knowledge. So, okay, so this is, this is very high level summary. And Leo was joking like this is, I spend a few minutes go over almost your 1 year of your calculus learning, right? So, but this is pretty much it. So remember, go back to definition, right? No matter when you learn any science and the math, go remember precisely what this definition really means. And then you have you build this along with build those, you can derive, if you try, go back to pick any functions and try to use that definition to derive you by yourself. You do a couple times, then you understand what it really means, then that become yours, right? Okay, then it's easy to handle understand the rest. Okay, good, cool. So now let's go back to what we can do. Why Isaac Newton needed to invent, Leibniz needed to invent this this look like complicated, a little bit complicated, fancy, and calculus. What is for? Of course, you can say, oh yeah, I understand, because if you give me any function, I can derive any location's slope. You give me function, I can derive any one underneath the area. And of course, I explained last time for Isaac Newton, when he started go to define the basic concept, just as simple as what is velocity, what is acceleration. He has to use go back to this definition, because velocity is really about the distance change rate over time, which is precisely needed to use calculus to define it. Derivative defined. Same thing, acceleration is really speed change rate at any moment. So that has to be used as strict definition. Otherwise, you cannot do it, right? So that is why Isaac Newton has to go through this one and to derive this whole thing, right? So let me go over some other things, other foundation, in order for you to so in order for us to really to be able to utilize. So there's certain things we have to go here, certain also some very simple relationship, right? So let's say go back to here. So by definition, this is derivative. And sometimes I use this sign, sometimes use this sign to represent rather than write this very simplified format. And so you can see, so if there's two function is plus minus relationship, and I want to get the derivative for the whole thing, it's really looking for individually derivative plus minus. Oh, you can write this way with a complete sign. Derivative the whole thing means derivative individual plus minus. This only apply to just like your 四则运算. So operation rules, and so this case is a simple, okay? Okay, but be careful. It's just only applied to this plus minus case, okay? And why is that? Okay, you can always go back to your basically the definition of derivative to prove that, okay? It's very easy, right? Because this one, the changing rate.
The area under curve 1 plus the area under curve 2 is equal to the area of curve 1 plus curve 2. Is it like that?
That would be the integral.
Because that's the integral. This is a derivative.
Oh.
Yeah. So this is derivative. So basically looking for the changing rate, the whole function over x, you're really looking for individual changing rate, adding them together. That's what this means. Okay. So you go back to the, Leo, you are seeing this. You are seeing this.
Yeah.
This one is what you mean. This adding together, you know, the area underneath equals individual adding them together. Okay. Yeah. So here, so let's go back. This one understand. So you have a constant time, a constant with the functions. The derivative actually is a constant you can take out and just derivative the function. Just increase 2 times and increase 2 times. So this one is, you know, this is same. So, and of course, if this function itself is constant, then the derivative is 0, right? Because, you know, it doesn't change. So the changing rate is 0. It's easy to understand. Go back to definition. So this is a, you know, x power n function. Its derivative we already know is n time. Put the n front and n minus 1. N is any number. Okay. So this is this you can prove that by go back to your definition. So here now the question here is getting complicated. You have to take some time to prove this. So it's 2 function timed together. You try to drive the derivative. It really is first one derivative time the second one original, then plus the second one first one original times second one derivative. So why this? Go back to definition. You know, if you like to prove that, go back to definition. So the change rate. So basically, you are go back to this guy change by delta x divided by delta x, and which really means f, you know, x plus delta x times gx plus delta x minus fx times gx divided by delta x, and then you derive this. Then eventually come to here. Okay.
Dr. Wang, could I add something really quickly?
Go ahead.
Okay, so I actually learned this formula in China, and what the teacher told me to help me remember it was 前导后不导后导加后导前不导. So 导 means like to take the derivative.
Right.
So if you treat x as like f as like the 前面那个式子 and g as 后面那个式子，那你就是前导后不导加后导前不导. So that might help.
Yeah. Okay. So now there's a division case is more complicated. So this one needed to do fx divided by gx derivative equal to, you know, on the bottom is g function square, and then on the top is still 前导后不导 minus 前不导后导. Okay. So those are the, you know, some of the operational, you know, rules, and you can individually prove each of them by go back to the derivative, you know, definition, right? Okay.
So our math teacher taught us like the way you remember quotient rule is basically high D low minus low D high over low squared.
Okay. Yeah, that's whatever, you know, you help you to remember. So then of course those are the one I already went through a little bit. The sine derivatives, cosine, you know, cosine derivatives, minus sine, and the tangent derivative is this, and cotangent derivative is this. And you can prove that if you like. And ex, the derivative itself, natural log derivatives 1 over x. And this one derivative actually is a little bit more complicated now, become this, and this guy is this. Okay, each one you can. So basically, people calculate, people proved, people take any function they can think about, and then they do this formula, and then they derive it, and then eventually become a new foundation can use, new formula can use. Okay, so that's it. And the same thing for integral. So integral basically has also set of the, you know, set of the whole rule. And for example, constant time the function integral, and you can take constant out, and you know, of course minus sign and take minus sign out. And if the plus minus integral is individual integral, and those are the one we already went through. And this one integral is really looking for someone's derivative is this function. And this guy's constant integral is looking for some functions, some things integral is constant, which is kx. Right? And the sine, cosine derivative is minus sine. So that's why this one integral is this, and this one integral is this. All those becomes existent for you as a library. Eventually, you will do. Okay, here is a little bit more complicated. I try to derive a function with a built-in function, and so this derivative actually is you are doing first you df function f to g derivative, then times g function to x derivative. So it's makes sense because it looks like you cancel this dg and the df dx. Okay. So those are of course it takes some time for you to digest, and then later on you can use it. Okay. So this is I just take a very quick overview of based on what we went through for the the definition, and go through this. Okay. So now I'm going to give you some practice, and so hopefully help you to master a little bit, and then we can go to next stage to try some interesting math problem or physics problem built on top of what we learned in the past 3 hours of 1 year's calculus content. Okay, got it?
And I think if you do have any questions, don't be afraid, because I can't imagine absorbing everything this fast.
Yeah, I agree. I completely agree. So if you got confused, you got something you don't understand, it's very natural, because we squeezed one, I wouldn't say 1 year, but half year things into 1, 2, 3 hours. So it's hard. That's why you needed to but at this stage, we have built enough. If you are able to grasp this knowledge, understand, to a certain degree, 80, 70, 80%, that's good. And so I try to build a math foundation, allow us to use it, to do other things. Where we continue to do some other things which will require this calculus knowledge, you are keep learning calculus. So don't be too much worried. Okay, good. So along the way, if you have any time you have questions, just let me know. Let all of us know, then we can go. Okay. So this is now let's do something simple. And for example, let's do something simple example, right? The first example I give you is right. So let's say I have a function gx equals to, and if you really like, you say y equals to x squared minus 4x. So this is if you learned algebra 2 or even algebra 1, this is a parabolic shape. So I want to know, so where is the maximum? This curve is like bell shape, either face up or facing down, and I want to know the lowest point or the highest point where it is. And of course, in algebra, you have to do like this. What do you do in the algebra? You're going to say, oh, I'm going to say this is minus 2 squared. Then I add 4, and I might cancel this 4, right? So this one, if you open up, will be this, right? So in that case, I know when x equals to 2, I have y equals to minus 4, which is the minimum, correct? So that's basically algebra, what algebra does, right? Got it? No question. This part Everybody should understand, right? Well, so now, and using, we just learned the, simple derivative. Can you do it quickly? Just prove, how just where prove is powerful, the derivative is. And this is just a very simple example, right? We can give you a much complicated example later, which will be hard to solve with your conventional algebra knowledge. Right? So everybody does it, try it, okay? So here is basically simple, dy dx. We just, try to, get derivative for this whole function, because the individual adding plus, we can do the individual and then add plus or minus together, just like we just went through this formula. So what is x power 2's derivative? We know it's 2x. What is minus 4x derivative? We know it's just minus 4. Got it? So this one, when this one equals to 0, means this kind of slope, this slope is 0, which really should be either maximum or minimum. Correct? This curve. So basically, this curve is like this kind of shape, and you are trying to finding all the slope. Slope is this function, and when slope hitting 0 here, that's only place slope is 0. That's your minimum. Or according to this case, only this place slope is 0 as your maximum. Okay, so in that case, x equals 2 is your either minimum or maximum. Even though by doing this derivative, you don't know this can be either minimum or maximum. You don't know which one is by just looking here. Correct? But how do we know it's a minimum or maximum by derivative without going back to our algebra knowledge? So if you call this W function, right? So you do one more time. You do, okay, let me do W to X again. This one, so basically you do the second time of this one, right? You did the first time derivative. This we call the second time. So basically you do again this. Sometimes we write this one called second derivative. So twice, okay? This one equals basically this function derivative, 2x, the derivative is 2. And this constant derivative is 0. So this one gives you do this slope. The function, the first derivative is slope. The second derivative time is slope's derivative. Is slope's change, and which give you a constant. It's a positive constant. So think about it. Think about here. You are getting us. So which case, as a slope's change is always positive. So here slope is here, right? Then slope is here. It's becoming smaller, correct?
Becoming larger, Dr. Wang, because it's
become larger because it's negative. This is negative. Here, this one slope is larger. This one becomes smaller. Smaller become 0. Become negative. Then become smaller. Even absolute value is bigger, but the negative is smaller. So this is increase, correct? From left side to right side. So that's why it's derivative again. So this is an increase. The derivative is positive. This one you say is a decrease from large, small, 0, negative, even more negative. So this one is going this way. So that's why this slope should be smaller than 0. So this really means this case is this case, not this case. So really means what we get here is minimum, not maximum. Got it? So that's so by taking another derivative can tell which direction. So that is a simple application of using derivative to solve this problem. Okay. Good. Okay. So if you just look at this case, you are saying, wow, I think my algebra knowledge is good enough. I can do as quick as you can do with derivative. So what? Why we need a derivative? Okay, if that's the case, I can convince you with another example. How about this? How about, let's say y equals to, we can anytime, we can write plus 81 x squared minus 42x minus 8. Write anything, you can write anything. So now it's cubic, or even power 4, power 5. Is that easy to solve with your algebra knowledge to where is minimum or maximum? Probably not, right? So let's try this one with derivative. So this is basically my question is finding this functions, maximum, minimum, maybe multiple, right? If the curve is going this way, then they have maximum, they have minimum, they have maybe another maximum again. You have several things, correct?
Wait, so Dr. Wang, do you want us to find the all local maximum, all local extrema? Or
yeah, sorry, local.
just...
Yeah, all the local.
Okay.
For absolute extrema, we also got to test the endpoints, right?
Right. Okay, so this case, give you idea. So you can simply do it, right? So basically, if you do is the derivatives here is this first term, because it's all adding them together or minus together. You can do individual. There's 24x squared, and the next one is put out 2 out x 42. Then the rest is 0. So this guy is the first derivative, right? So of course you can do the second derivative again in order to make sure which place is minimum or local minimum or maximum. So you do it again, that's become 48x plus 162, right? You have this one, right? So this case you can find what x. There's two, basically there are 2x. One x1 equal, I think x1 equals to -7, x2 equals 1/4, and so there's two place is either showing local maximum or minimum. Then you put this one back, you can know if this location y second time is larger than 0 or minimum 0. So in that case, so this one eventually proved to be maximum. This one is minimum, because this place you put here is smaller than 0. This one is larger than 0. Good.
I have a question. So can I understand derivative, which is what we're doing right now? So can I understand what we're doing right now is as if we're making this, let's say it's x to the cubic, and then we're making it x to the square, but then we make the number in front of the x larger by like 3 times, by the 3 times go to the cubic. Can I understand it like this for now?
Yes, so yes, you can. That's arithmetically, that's what you're doing. But if that's the sole understanding that you have of how to take a derivative, then it can prove problematic when you're asked to explain what's happening, right? What this is saying essentially is that if you had the function ax cubed, and you tried to create a function for the slopes of ax cubed at every single point, then you would yield the function 24x squared as the function for the slope of ax cubed. Sorry, you would get 24x squared as the function of the slopes for ax cubed at any point. So that's conceptually, that's what you're doing. But yes, you're right. When we do arithmetic, it's sort of just like you pull the 3 down and make the exponent a 2, and then you multiply the 3 by the 8.
That's magical.
I think that's more of like how you solve the derivative instead of like what it actually means, because what you said is essentially like power rule, which is a handy tool that we use it to solve it, but that's not like why derivative exists, or like how it like its principles. You know what I'm saying?
But I still have a question about, like, for instance, so how can we prove that 24x squared is the slope of every point of 8x cubed? How do we know that?
So Dr. Wang had introduced at the beginning the definition
Concept. You have to go back to concept. So
Yeah.
you didn't, so basically you didn't understand our last class. That's why you have this problem. So last class, I was, so basically, hold on.
So he had, Dr. Wang had recapped that it was like delta f of x over delta x. That's the definition of a derivative. Like the change of this function over the change of like this small domain interval. And if you plug in 8x cubed into fx and then did everything out, then you would eventually get a proof and you would eventually yield the answer 24x squared. Dr. Wang had also sent into the group chat a proof of sine and cosine. So you can walk through the same process with just the cubic function instead of the trig function.
Right, so you have to, for Paul, you have to go back to the definition. What is derivative definition? You have to take one function like x squared or x cubed. You have to do yourself before you can truly understand it, okay? I don't think you have done it. So you have to do this before you understand. You cannot just watch my video, think you understand everything. There's no way. That's not the way you learn math. That's no way you learn the science either. Okay, you have to do it yourself. When you have to turn the paper back, and now starting from a blank to do it yourself. Once you are able to do it independently, then you understand. Otherwise, you don't. Okay, that's how learning is like this, right? You got it?
Got it.
Yeah, so you have to derive this by yourself. It's really important. That's why I go really, lightning speed, right? I go lightning speed. I try to squeeze everything. So that's why I require you to really solve, for example, I look like I did here very simple, but for you, if you haven't done this, it's not that straightforward. You have to do yourself, and you have to go through what I go through step by step before you're really able to master it. Okay, so here I only show you something, and of course it's much easier for Leo and Frank, who has got some of the calculus knowledge, to understand right away. But for you never learn it, you have to go back to fundamental. Okay, otherwise it's really hard. You got lost. One more lesson, you completely lost. We're probably halfway into in another 10 minutes, you're going to completely lost. So that's very dangerous. Okay, because eventually you are fun, you 变成听天书了. Okay, so you have to go back to step by step, and you don't need to prove everyone here, but you do need to prove 1 or 2. Understand? You have to do yourself 1 or 2 to make sure. Oh yeah, now I understand what it really means. You give them another function. Maybe you did here, you still couldn't do the sine function, sine x. It's normal. The sine to prove sine x, the derivative is cosine x. It's not that easy because you encounter lots of other issues. But that's okay. Okay, that's no big deal. And then you are saying, oh, okay, other people prove that, I'm going to use it. It's fine. Of course, it's good to you try to understand how this getting here, but you don't really need to understand you don't need to prove every single functions listed on the textbook or somewhere. It's everyone you have to prove by yourself. But at least you have to do something, and to prove yourself, to show, oh, I truly understand how this process goes, right? How this, because that's help you to understand the definition. Otherwise, you don't even understand the concept, right? So that is becomes really, really dangerous. Got it?
Got it.
Good.
Thank you.
Okay, so my next example is going to be, like, let's do a simple thing using integral. This is a circle, right, with a diameter r, right? Is the center of the circle. You know the area is pi r squared, right? So let's do using integral, because integral means here we have a curve. Integral can help us to build all the area underneath, correct? So in that case, so knowing this is a circle, knowing this is circle, can you prove the area is pi r squared? So look like we are using 杀鸡用牛刀, right? But this is good example actually to show you, and later on we will have more fancy example. But here, can everybody try to do that? There's two different ways to solve this one. One is much simpler. One is much little bit more complex. But there's two different methods. So method 1, method 2. Okay, I'll show you both methods how to do this. And but anybody want to try? Of course, in order to solve the area underneath, you need to know this function.
So basically, standard equation of the circle.
Yeah, standard circular equation means x squared plus y squared with the center at 0 equals r squared, correct? So that is a circular function, right? So describe this curve, right? So really means y equals to what? Y equals to r squared minus x squared. Of course, there's positive minus, but look, we only needed to solve this 1/4 of that, right? The rest is times 4. Let's just solve 1/4. We don't need to deal with x equal. We don't need to deal x or y negative thing. We only deal everything from 0 up. Okay, so this is this curve function, correct? So let's solve it. So how to get the area? The area is this y, right? This is y. So area is, we call it a. A is really integral this y x from x equals 0 to x equal to r, correct? Right here. Or it's hard to understand this way, or you can understand it's really a sigma. Go back to our definition. It's really a sigma, right? Those tiny slices, right? With location x, and of course width is delta x, and at this axis, this location is y. So this slice area is width times height. Height is y, width is delta x, right? Then you adding all those pieces together from x equals 0 to x equals to r, right? Of course, delta x has to eventually go to limit 0 in order to make this be accurate. So that's your integral definition, which is coming here. Got it? Or this becomes y is here, right? Y is here. So this becomes square root r squared minus x squared. That is y, correct? And dx. So that's it. So that is 1/4 of this one times 4. This one times 4 equals the whole area of of the circle. Correct? That's it. So how to do this? How to do this? Now I getting complicated, correct? Okay. So I show you a very simple method to do this integral with everything we learned so far, okay? So it's here. So this kind of integral, I want to use basically I assume x equals r times sine theta. Okay. So in that case, x squared equals r squared sine theta squared, right? And then dx. So basically, you can say delta x equal to what? Delta x equals to. So this is here is a little bit jump. Two people. I think someone be knocked out. Yeah, I think several of you keep falling off. Paul has a little bit problem coming on. Jenny, are you on? Jenny, are you on?
Yeah.
Okay. Yeah. Okay. So basically, I realize I probably need to jump a little bit. So here is basically equals to cosine theta delta theta. So here, translate to here, we needed to be more explanation because you don't have enough calculus background to understand this. So basically, small delta x equals cosine theta. So this one will come back to explain to you. So if you put this one, everything back to here, so that becomes that becomes 4 0 to r integral. So basically it becomes, you can take r square out, take r, inside is 1 minus sine square, and the dx meaning r times cosine theta d theta. So that becomes 4r. R is constant because that's the diameter, radius, sorry. So this one becomes, we will change this later because now, so this one is cosine 1 minus sine square, sine theta square is cosine theta square, and after square root is, because everything is positive, here is cosine times cosine d theta. So this one becomes 4r squared. So for x equal to 0, theta equal to 0 angle. For x equal to r and theta equal, sine theta equal to 1 really means pi over 2 theta, right? Sine 90 degrees is 1, sine pi over 2 is 1. So that translates from x trying to the theta, basically, because now we are integral theta now. We already changed from integral x become integral theta. So this one becomes cosine square theta d theta. Okay. And the cosine, if you so if you have learned the trig is cosine 2 theta equals, I think is cosine 2 theta equals 2 cosine square theta minus 1, I believe. Yeah. So then you make it back 4 square. So this one becomes 2, basically cosine 2 theta plus 1 divided by 2 d theta. So this one, this 2 cancel, 2r square cosine 2 theta d theta plus 2r square 1 d theta. So this one you can see equals to pi r square. Okay, this one actually you can prove that is equals to 0 because sine theta is cosine theta, sine theta the derivative cosine theta, and then you can calculate 0. So that basically leading to the proof of the area is pi r square. Okay. So now let me go back to, I want to, I don't want to go too fast here, and let's go back to little bit about why there are a couple of things here I need to further explain to you because otherwise you get confused. So let me see, let's go back to step by step one more time, okay? So because we want to calculate the area underneath this curve, which is described by a function y equals square root r squared minus x squared. So this function, the area underneath, so we are basically doing this function's integral from this location to this location, integral cross x. Basically, we're moving, we are adding up those little p's at, now this piece at x location with delta x, and at x location the height is y, so the area is y times delta x. Then and another location the x keep changing, y keep changing, but we add everything together from x location 0 to x location r. So that gives you the whole area. So that is what eventually becomes A equals integral from x location 0 to x location r, and this functions, this y times delta x, which is what I just said. And then of course I time 4 here is because it's a 4-piece, and it's nothing to do with here derived itself. And then this is a y function, delta x, right? So integral from x equals 0 to x equal r. So in order to integrate this function, I did some mathematical treatment. So I assume x equals to r times sine theta. Okay, so then I put this back, put it here back. So in that case, x squared equals r squared sine theta. You see why I want to do this? Because I want to remove this square root. So in our case, r squared minus r squared sine theta squared equals to r squared times cosine theta squared. So in that case, I can completely remove this one, leading to a trig function. And but here, since I removed, I switch x to r to theta from here. So I also need to switch delta x. So basically now, when x equals to r sine theta, right? So I was doing delta x integral. Now I need to do delta theta integral. So why? So how do I change? So how do I, if x and theta with this kind of relationship, how I can change delta x to delta theta? Well, delta x, if I can get delta x over delta theta, if I can get this one, then I know the relationship. If I can get this one equal to something, then I know delta x equals something times delta theta, correct? Then I finish this kind of translation. But how I get this one? Well, this one eventually, of course, everything, delta theta also, delta x, delta theta both equals to 0. Really, I was doing delta x, delta theta. So that's really doing this guy's derivative, right? So that's why this guy's derivative equals to r is constant. You can take out. I'm doing sine theta's delta theta. Sine theta is cosine theta, correct? This function derivative. So in that case, that's why delta x becomes r cosine theta delta theta. So that is exactly what I'm seeing here. Yeah, I jumped over too fast, go over this process. So once we have everything here, we have how to convert x into theta, how to convert delta x into delta theta. So I put everything back. So now I have here, convert everything. So meanwhile, I have to also convert here x to theta because here it means x equals 0 to x equal r. So in that case, when x equal to 0, from here, I can know theta equals 0. X equals r, here I know sine theta equals to 1 means theta equals to 90 degrees of pi over 2. So that's why I eventually also translate this part to 0 to pi over 2. So that is exactly like x equals 0 to r. So in that case, I do this conversion. I completely the whole conversion. And now I go further move down and I have r taken out, which is constant. And now I have this guy is cosine theta because 1 minus sine square theta equals sine square theta and the square root cosine theta. And this guy, no, oh, this two constant take out. So this cosine theta again, delta theta. So now I'm converted to integral of cosine squared delta theta's integral. And because I don't know how to integral, I know how to integral sine theta and cosine theta, but I don't know how to integral cosine square theta. So I use trig knowledge again. Cosine 2 theta equals 2 cosine square theta minus 1. Then I were able to convert this one into a power 1 theta thing, right? Then because this is addition, then I separate those two parts. One part is simply just a simple integral, and this part is dealing with cosine 2 theta integral, right? So now, so y 0 to pi divided 2 cosine 2 theta integral to d theta equals to 0. Why? So why this part equals to 0? Because if this one equals to 0, this piece gone, and we only left this piece. This piece is really integral 1, right? Integral 1. I didn't write 1 here, right? Integral 1 integral is whose derivative is 1 is theta. X derivative is 1. Theta derivative is 1, right? So So in that case, it's a theta. Theta from 0 to 2 pi, and the change really means, pi over 2, 0, 0. So pi over 2 times this guy is become pi r squared. Oh, I jumped too fast. Let me do two things. I try to explain. I get everything explained. One is 1 times delta theta from 0 to. So what this one equals to? Well, we know this guy's integral equals to theta, because theta's derivative to theta is 1. So this one becomes from 0 to pi over 2. So that means pi over 2 minus 0 equals pi over 2. So that is y here is equals to pi over 2 times 2 means pi r squared. But this section give you a surface, a sphere area, circle area pi r squared. So now I have to prove this part equal to 0, then I have perfect everything. So now why is this part equals to 0? Okay, let's go to here. So 0 to pi over 2 cosine 2 theta d theta equals to what? And I can put 1/2 at the front, then I can put a 2 in there and move the 2 into here, d2 theta. Correct? Now it's based cosine 2 theta d2 theta. So in other means, I convert 2 theta into x dx. So what is cosine? So basic is sine 2 theta, derivative is cosine.
Dr. Wang, you might want to tell them what a U substitution is.
Yeah, the substitution is easy to understand, but I quickly do a substitution. So this one from 0 to pi over 2, you will find out sine 2 times 0, sine 0 is 0, sine 2 times pi over 2, sine pi is still 0, basically still 0 minus 0. So this is why this one equals to 0. Okay, so that explained why this one equals to 0, this one equals to pi over pi r squared. So that eventually give you the whole circle area is pi r squared. So this one went through a pretty lengthy of proof. I basically did simple and integral of a circle area, right? So by using integral. So of course this is really the first true example you are exposed to using calculus to do something real, right? Other than some of the maximum minimum, the derivative thing we just did. So this is the first example you're really using integral to using calculus knowledge to deal with a simple thing like here, right? It looks like it's 杀鸡用牛刀, right? However, it is something, and it can demonstrate later on is once this whole thing look at to you first time to learn calculus is complicated. However, later on you find this is really powerful too, and it can do much complicated thing which you are not allowed to do, you are unable to do without having the calculus knowledge. But I give you a much simpler proof, method 2 here. I give you a much simpler proof, another method to prove this one. Do not go over such lengthy things, but still do the basic thing. Same. Now let's go back here. So we have a circle, right? And so we have the circle with radius r, right? 0, so r, okay. How I can find another way to use integral to get the area? So before I was using I was using XY system. So I have this formula, this function. I have to do the integral of this slice along a curve, circular shape to do the integral. So can I find the other way to do it? Yes, you can. For example, you can say, oh, because it's a pi, it's a circle. So why don't I integral this tiny slice? By integral the whole, by doing a slice by slice this way, I integral the whole thing, then I can also get the whole area underneath this curve, right? So how to do that? So let's finding. So this is place. This is a place, a tiny slice. Eventually, the slice, of course, has to go to infinite small in order to make this area accurate. So here is angle theta, right? So this is our R radian, correct? Okay. So how to write this slice? Of course, in this case, this angle is third theta, correct? This angle is third theta. So how to write this slice area? This tiny slice area, so area of slice equals to what? The area slice is theta theta angle, right? So really means theta theta divided by no, this slice angle is basically approaching, you are using this slice angle is like a triangle. So basically 1/2 base time height for this slide. So height is what? For this slide, height is R, right? Correct? This slide triangle, right? This is this slice of triangle. I mean, not the exact triangle, but it's my piece. So this one, looking at as a triangle, is really basically is 1/2 of base time height. So, or 1/2 this arc time height. So in our,
Dr. Wang, there's an assumption here that like because your d theta is so tiny that the arc there is essentially, you can assume that it's like pretty close to a straight line.
right.
So that's why you can assume that it's a triangle.
Correct. Yeah, that's assumption. So because the infinite small, so in that case, it's basically 1/2 of the height is R. Base is R time theta theta. So this arc is R time theta theta. So that gives you 1R squared theta theta. So that is the area of this one. So then you do an integral. This you do everything together. Is basically now this area equals to, you do this guy's integral from theta from 0 to 1/2 pi. This is, of course, I have to time 4 in order to make it the full area. So this one is quickly, because this R square is constant, is 2R squared is theta. So this one, we already did this one before, equals pi divided by R. So this one becomes. So this is a very quick proof of by using a different system. So that quickly proves that this is pi R squared. Any question? So the only thing, of course, you need to understand that this is this is tiny triangle base time height divided by 2. So that is 1/2 r divided. Base is this tiny thing. Height is r, and the tiny thing with angle delta theta. This tiny and the radian. This tiny is r times delta theta. That's it. Any question? So this is just a pretty simple calculus application, and which sounds fancy, and but of course, 杀鸡用牛刀, right? So basically, why you use this so complicated? Try to prove a simple pi r square, and it's meaningless. I agree, it's meaningless. Just learn how to use it. That's it. Try to show you how to use it. Now we can go to something you may not be able to do without a calculus knowledge. See how to do that. So maybe I should give you this as a homework, but anyway. So basically now let's deal with a sphere. Sphere has a radius like ball, right? Like radius r, and how to derive the surface area of sphere is eventually 4 pi r square. 4 pi r square. And how to derive volume of sphere eventually to be 4/3 pi r cube. So you can go over the calculus and derive it, and the similar thing. So here this case you only need you only need a few lines. You can quickly derive it, and also you only need a half page. You can derive it here. So for both the sphere's surface area and volume. Okay. So I think you have this page on the PDF I send you the document. But if you we can try to next time. Today, we are 11 now, a little bit over 11. So I want you to digest what I went through today, and before we move faster. And I know many of you probably confused by many things here. I understand it's a pretty quick jump. If you are able to do if you are able to do this and this, is pretty, your calculus pretty advanced already. So Leo and Frank, based on you have learned 1 year calculus, right?
Yes, and Leo isn't able to join the call right now, but
okay.
But yes, I wouldn't. So we didn't, because this involves things like Dr. Wang did a substitution there. He did some implicit differentiation. He also used polar calculus, which we didn't learn until the 3rd term out of 4 terms of calculus. So like we were 3/4 of the way through calculus.
We are 3 hours into 4 hours into this, or we did your 3/4 years stuff. But anyway, yeah. I understand. It's challenging. It's difficult, and but I don't need you to be 100% clear on everything. But I need you to roughly be able to follow, because when we do further example, you are keep learning, keep catch up something, and but meanwhile, I really want you to ask questions, and I'll review this recording, and And sometimes you may want to go to some YouTube, some lecture to repeat some knowledge taught by another teacher, and so that help you to get more. But I do believe if you are able to follow this, and it will help. Of course, the whole purpose I'm doing here is not really just teach you math, because I really need some of those knowledge going forward to do some physics problem and some of the science problem. So that's the reason, right? We are here, right? I'm not here just for the purpose of teaching you math, this purpose. But math is just a tool, but this tool is so important. So that's why I have to go over this, and also unfortunately go over with a lightning speed, because otherwise we were become a 1 year math class rather than doing other things. So that's unfortunate, but I hope you are, if you have any questions, just give me a call later, or we can go explain a bit more in detail. I'll go over. If you have any question, if you do some calculation by yourself, derive what step by step, because that's very important. If you don't do it, you won't be able to truly understand it, and until you really take a blank piece of paper, doing everything from beginning, and you won't be able to fully master it. Okay. Or at least master to enough. So this is something we are continue. So once we pass over this phase, I will try to. So later on, for example, maybe in the next couple lesson, I'm going to show you. So using this simple calculus, how to prove refraction law. Right, so we call Snell law. So that's a basic physics. So light coming in, and the interface with interface. So one side, for example, is air, the other side is glass or whatever, and then the water. So if you stick, if you put a chopstick into your water cup, and you will see this it start to bend. The reason it's bend because the light is bending once it enters the water or glass. And why is bending? This is called, this bending angle calculation is called Snell's law. It's basically a very simple formula like here. So it's N is we call it refractive index times theta 1 equals refractive index 2 times theta 2. This is a very famous called Snell law. So why there's Snell law? This how to derive the Snell law? I'm coming here from from a very simple simple calculus derive the Snell law. Okay, so basically Snell law is basically to say very interesting. This is very physics, how pretty physics is. It's coming from this position in air, light travel to this position in water or glass, and basically try to say, of course, light travel in one medium is always straight line until the hit another medium go to again straight line. How the straight line is bending, right, at this interface. So why is bending? Why not just go continue straight line? So that is because if you say from a point A travel to point B, and there are infinite paths, right? You can say you can go just a straight line A to B, and you can say can go this way and go this way, or go this way, right? So that it's every path you still go straight line in your own medium until you hit the second line. So why the light shouldn't go just keep going straight line between the two medium, keep straight line all the way to B, rather going this? Oh, it's because light travel in different media speed is different. So that's physics. So light travel in air, in vacuum is one speed. We already know, like 2.99 times 10 to power 8 meter per second. And but in the glasses, light travel slow down, or in the water slow down a little bit. And because they slow down, so they have to bend in order to make sure A to B is the the fastest way. It sounds really weird, right? Why not A to B is a straight line? Shouldn't the straight line the shortest or fastest way? A to B is a straight line, is the shortest way by geometry, but it's not the shortest line by physics. The reason the physics is counting on the time. From A to B, how long time able to reach B? If you realize actually by doing this kind of bending, you are able to reach B faster than going straight. Interesting? So that is, yeah, one of the physics principle. So I will try to later on show you once you have. So of course, this one required to calculate the time in each of this transition, adding of the total time, and because we needed to find to minimize this travel time, and we go a simple derivative and let the derivative equal to 0, finding one of the minimum of the travel time, then eventually leading to that law. Yeah, this is a simple, calculus application, derivative application, try to derive one of the very famous physics law called the refraction law. Okay, refraction law basically saying that from A to B, when you're passing between different medium, and the physics always looking to the shortest travel time. So most efficient way. So that's physics. Physics is very simple, right? The reason we release a ball, the ball we're going to hit the ground, fall. Or in a ball, you release ball from the edge. The ball will be swing in the ball, eventually rest at the bottom ball. It's also same thing. It's because they want to minimize the potential energy they call. So here is trying to minimize the travel time. Well, that's what God designed the world to be. The God tried to design the world follow a principle called the minimization principle, minimal principle, that called the Fermat principle. Fermat principle means so the world is operate in the minimal energy, minimal travel time, the most saving way. So that is physics. So it sounds very interesting, isn't it? So why God designed way? Well, God doesn't want to waste anything. God want to light travel from A to B the fastest way. So that is how they design the world. So anyway, those are just a little bit hint for what we're going to learn, to learn going forward, which of course require a little bit of math knowledge, unfortunately. And that's why I try to squeeze 1 year of math, pretty advanced math thing within a few days content. Okay, anyway, that's hope you enjoy it a little bit, at least not complicate your interest, confuse you completely. Okay, thank you so much, and yeah, talk to me if you have any question. Don't be scared if you only captured the 10, 20, 30, 40% of this, because just like Frank said, is this gigantic knowledge. Typically, you need to take much longer to digest anyway. Okay, cool, good. Okay, thank you so much. I'll see you later. Okay, bye-bye.
Thank you.
Bye.
Bye.
Bye.